So we're working on calorimetry experiments now, and I want to show you a technique for solving calorimetry problems that a lot of my students have found helpful. Calorimetry problems aren't difficult in and of themselves, it's just that there's a lot of information to keep track of. And sometimes putting these into a table makes it a little bit easier for you to be able to keep track of all that information. Now, I sent you a video that hopefully you watched yesterday on calorimeters and what they look like. And the gentleman in that video specifically mentioned that the heat that is lost from the hot object that you put in there, or from the reaction that takes place in there, all that heat has to be absorbed by the water. So whenever you do a calorimetry experiment, there are only three things to keep track of: the calorimeter, the liquid, which is generally water, and whatever object you put in there if you're dropping an object in, as opposed to actually running a reaction in the calorimeter. The problems that we're starting with are going to put a hot object into the calorimeter, specifically a piece of metal, often because we want to determine what that metal is, and we do that by finding the specific heat of it. So those three things are what we have to keep track of. And I am going to actually show you example 13.2 again, but I'm going to do it using a table so you can see how this table works and to see if you think maybe it would be a little easier to work the problems in that way. So if you look at the table that I have back here on the board, I have three lines going across. One for the calorimeter, one for the liquid, which in, again, most cases is going to be water, and one for the object that you put into it. All of the pieces going across just come from the heat equation, Q equals mc delta T. Now I've flipped it around the other direction, and so here's the M for mass, the C is right here for specific heat. The delta T, I've broken it down because I'm going to have an initial temperature and I'm going to have a final temperature, and from those two I can then calculate the delta T, and then my Q will go in the last column. So the thing that you have to remember about this is that the calorimeter and the liquid, whatever heat they gain has to have come from the object. So let's walk through an example here and I'll show you how to do this. Now, what we're going to keep in mind here is that in this very first problem, he tells us that we can ignore the heat absorbed by the calorimeter. So for this particular problem, I can just basically ignore this part of the table. All right, so a 45.9 gram sample, this is on page 396 in your book, of an unknown metal is heated to 89.7 degrees Celsius and dropped into a calorimeter that contains 150 grams of water. The initial temperature of the water is 25 degrees Celsius, and by the end of the experiment, the temperature increased to 26.9 degrees Celsius. What is the specific heat of the metal? So what we're going to do is we're going to start back again at the beginning of the problem, and we're just going to fill in each piece of information that we know. So it says a 45.9 gram sample of an unknown metal. So that means I can go right in here. The mass of my object is 45.9 grams. Is heated to 89.7 degrees Celsius. Well, that's going to be the initial temperature. So I have 89.7 degrees Celsius here. And dropped into a calorimeter that contains 150 grams of water. Okay, so that's my liquid, 150 grams of water. The initial temperature of the water is 25 degrees Celsius. So that will go here. And by the end of the experiment, the temperature increased to 26.9 degrees Celsius. What is the specific heat of the metal? Ignore the heat absorbed by the calorimeter. Okay, so I am looking for this piece right here. Question is, do I have enough information to find that? Well, you do, because for one thing, we were told that the liquid is water, and we know that the specific heat of water is 4.184 joules per gram per degree Celsius, so I can fill that in. Also, the final temperature of the water is also going to be the final temperature of the metal, because you're going to let it sit there until the heat has been transferred and you come to a temperature that is no longer changing. So you've got 26.9 degrees Celsius, okay? Now, if I know an initial temperature and a final temperature, I can calculate a delta T, because remember, delta T is final temperature minus the initial temperature. So 26.9 minus 25 gives me 1.9 degrees. I can also find that down here. 26.9 minus 89.7, that one's going to be negative. And so that's going to be 62.8 degrees. Just as a point of a way to check yourself, part of your temperature changes should be positive, part of them should be negative, because if you're going to gain heat, you've got to have gotten that heat from someplace, so that means something else had to have lost heat. So now, if you look up here, I have enough information to be able to calculate the amount of heat that the water gained, because I have the mass times the specific heat times the delta T. So I'm going to take 150 times 4.184 times 1.9, and that will give me, to two significant figures, 1,200 joules. Now, again, a calorimeter is insulated, and the whole purpose of it is designed to keep all of the heat inside the calorimeter. So if this is the amount of heat that the water gained, that has to be the amount of heat that the metal lost. So all I'm going to do is I'm going to take this same 1,200 joules, and now I'm going to make it negative because the water gained it, but the metal lost it. So now I have a Q, and I have a delta T, and I have an M. So if I take 1,200 divided by negative 62.8 divided by the mass of 45.9, that will give me C. And so if I type that into the calculator and divide it out, you will end up with a heat capacity of 0.42 joules per gram per degree Celsius. And that answer should be the same one that he got, and it is. So we know that we did it right. If you're going to use a table like this, you don't really need to write out all of the equations, because it's pretty obvious where all your numbers are coming from. The one thing I would caution you about is that when you multiply the numbers out, make sure that you're multiplying the delta T and not the initial or final temperatures, because those aren't in that heat equation. So just make sure you're using this column, and this column in order to find Q. Okay? So if you don't have to use a calorimeter, if you can ignore the calorimeter in the problems, that's the kind of problems that we had today. And then the next time we'll talk about what to do if you need to include the calorimeter in the problem.